In this screencast, we're going to review multiple linear regression, and then I'm going to show you how we can use something known as the matrix approach to solve for the coefficients in a multiple linear regression model. Towards the end of this screencast, we're going to be working through a problem in the back of your book. We wish to develop a multilinear regression model that relates the inputs. We have age, the severity of the illness, whether or not they had a medical procedure, and anxiety to the output, which is satisfaction. Note that the third column here is something known as a categorical regressor. It's either a 0 or a 1. In regression models, in addition to continuous variables, we can include categorical regressor variables. In a multiple linear regression model, we have multiple inputs. We have the 4 inputs here. X1 is age, X2 is severity, X3 is whether or not they had a surgical or medical procedure, anxiety is X4, and satisfaction is our output. Here, I've just set up a simple multilinear regression model where we have the output is just some function of each of those variables, X1 through X4, multiplied by coefficients. We have an intercept, beta naught, and then we always have an error term on the end. The error term, epsilon, just represents random variation in our data. One of the most basic multiple linear regression models is shown here, where again, we just take coefficients and multiply them by our variables. We don't have any polynomial terms. We don't have any interaction terms where we're multiplying x1 and x2, although you can certainly add those terms into a model if you want. This variable k just represents the number of regressor variables. In the example we're going to be solving, we have x1 through x4. So k represents the number of regressor variables. In addition to beta 1 through beta k, we also have beta naught. And so we can always add 1 to our value of k in order to give us p, which is the number of parameters in the model. So if you have k regressor variables, then you have k plus 1 equals p parameters in your model. By the way, polynomial models are considered in your text to be multiple linear regression models. We have a third order polynomial model here in a single regressor variable, x, but your textbook basically says if we let x1 equal x, x2 equal x squared, and x3 equals x cubed, as just one example, then we can turn y into a multiple linear regression model. So just keep that in mind. Everything we're doing with multiple linear regression models, you can apply easily to polynomial models. It's quite common to rewrite our regression model in matrix form. Y equals capital X times beta plus epsilon. Here, y is a vector of our observations. So these are our experimentally determined observations. X is our model matrix. This represents all of the inputs that go into each of our observations. You notice here, and this is really important, the first column of X is just a bunch of Y's. And the reason for that is if you take a look at our model parameter vector, which starts with beta naught, when we multiply array X by vector beta, the first element of each of our equations is beta naught. And so the coefficient that we want to multiply by beta naught in our X array is simply 1. So it's really important to include this column of all ones in your model matrix X. And then we also have a bunch of random errors, epsilon 1 through epsilon n. And n here is the number of observations. Similar to what we did using simple linear regression, we're going to calculate a sum of squares, L, and we want to try to minimize that. The least squares estimator, beta hat, and beta hat here is a vector that contains all of our estimates for the parameters in our model, is the solution for beta in the equations where we take the partial derivative of our sum of squares with respect to each of our beta terms, and we want to set those equal to 0. So essentially, we've got a bunch of equations that we're setting equal to 0. Through a bit of calculus, we can come up with something known as the normal equations, shown here in vector form. By the way, sometimes you'll see me write this as x transpose. That's the same as x prime times x times beta hat equals x transpose instead of x prime. So these two are equivalent. If you solve the normal equations for beta hat, remember beta hat is our estimate for all the parameters in our model, and beta hat is a vector. That equals x transpose x inverse. We multiply that by x transpose times y. And so this is how we can calculate our regression coefficients in our model. And again, you might see me write this a little bit differently in some of the workshops and presentations in this class. This matrix equation provides the values of the model parameters that minimizes the least squares. In other words, this gives us the best model for our experimental data. So let's go revisit problem 12.9 in your textbook. Again, we're trying to create this simple multilinear regression model where we have 4 regressor variables, x1 through x4, and we have 25 observations. In a starter file called satisfaction data starter1, I've got a bunch of our data here, and I've got some equations that we're going to be using. In the next screencast, we're going to use these other equations. In this screencast, we're only going to use one of these equations, other than the model equation. In a tab down here, I have the regression output. So I've already performed this multilinear regression model in Excel's regression tool. And we'll compare what we get using the vector math to our coefficients here. So we're basically going to be calculating beta hat, and I'm just going to refer to this as beta, the coefficient vector that leads to the best model. In order to do this, we first need to calculate x transpose. That's what x prime is. So I'm going to go ahead and put in an xt here, just a label. Before we do that, it's really important to do a couple of things. First, I'm going to name this output data. I'm going to name that y. I'm also going to add in, this is really important if you're doing this using matrix math in Excel, we have to insert a column and we're going to have just a bunch of ones. So I drag that down, and now what I can do is I can take that column of ones combined with all of our input variables, and this represents our capital X array, so I'm going to name that capital X. Now I'm ready to calculate the transpose of X. If you have Excel 2019 or Office 365, it's really easy because you can just type in transpose of X and you can press enter. Otherwise, if you have an earlier version, you have to outline here a 4 by 25 region, and then you have to type in equal transpose of X, Control Shift Enter. And you're going to have to do that for all of the other calculations too. But with Excel 2019 or Office 365, they've made a couple of improvements, and you can just type in a single formula in a single cell. So now what I can do, I'm going to go ahead and name this, Control Shift Right. I'm going to go up here and name this xt, that's x transpose. Now we need to calculate xtx, x transpose times x, that's this little bit here. And I can use the mmult function in Excel, xt multiplied by x, press enter. So that's our xtx, and I'm going to go ahead and name this in the name box, xtx. We now need to take the inverse of xtx, so I'm going to call this xtxinv. That's simply the minverse, matrix inverse, of xtx, and we get our inverse there. Now what I need to do is I need to calculate x transpose times y. That's the rightmost part of our beta hat calculation. I'm going to put that over here. So this is xty. Let's first go ahead and name this xtxinv. xty is just the mmult. We're going to multiply xt with y. I can press enter. And finally, I can calculate beta. And this really is beta hat, but I'm just going to put it in as beta. Let's first name this vector, xty. Beta is simply the product, so I'll do mmult, of xtxinv with xty. And when I press enter, we get our coefficients. So essentially what this means is that's beta naught, that's our intercept, beta 1, that's the coefficient here of our x1 term, or our age. And then we have beta 2 is negative 0.59, beta 3 is 0.41, and beta 4 is 1.31. Let's compare these values. So I'm just going to go ahead and copy. Let's go over to our regression sheet, and I'll just paste them over here on the right. And you see that they align nicely. So this is how Excel's regression tool is calculating the coefficients for a multilinear model. In the next screencast, I'm going to show you how we can perform statistics on these different parameters so we can get a standard error for each of our beta terms. And then later on, you're going to learn how you can use those standard errors in calculating confidence intervals and performing hypothesis tests.